Okay, time to continue. So let's see. We were at loops, right? Here we go. One back. While this is sorting out, so I fixed my code eventually, so it was before the break like this. The mistake I did is I didn't put brackets for the function call of enumerate. And after this is finally working. Now, the meaning of enumerate is it's actually creating a pairwise iterator with the number of the element and the element itself. So in principle, I shouldn't even need this now. Let's see. There we go. So once over-engineered and now back, and now I have an inverted dictionary to the one before. So first I have the names and then the numbers, and down here I now have the numbers and then the names. Good. So go back to the for loops. So we talked a little bit for loops. We had one example. And at the bottom here, I also give enumerate. Nope, not scroll down. But enumerate is a useful keyword or function here with a syntax followed by a list of an iterable object. So let's play around with this a little bit. So just now we already saw a list of cities. Scroll down. Enumerate example now. Enumerate. I plug in a list, right? I execute. What do I get? Something that is yet to be called, right? So I take this object and put it into a list. So whatever enumerate created, right, is being called in list and made into a list. Okay, and my list is a list of the round brackets is what? What's a round bracket? List, tuple, set, or dictionary. If you don't know that it is a tuple, then you can just take one of the elements, put it into the type function, and it will tell you tuple, right? But the nice thing about this is, so this is a list here, right? Sorry. Of pairwise elements. So it has the cities inside, but it also numbers them from 0 to how many you have. That means you actually can use them in a for loop as well. Because we have two values after the enumerate created the iterator. We have now two iterators, I and j. So we enumerate over this and say just print I, comma, is for not too many fours, means, and then we put the j here. Invalid syntax. Oh, I forgot the in for I in. Okay, so 0 is means English. 0 means Taipei, 1 means Kaohsiung, 2 means Tainan. So far, so good. And I can do this because I takes the index of the iterator, so 0, 1, 2, 3, and so on. And j takes the actual value that is provided in the list. And so here Taipei, Kaohsiung, and Tainan. So far, so good. So alternatively, right, if you don't want to work with enumerate, there is one option. It's a little bit more cumbersome because you will need to use range of the length of your list, and then pass the index I, right, the iterator that then becomes an index. If you put it into the list of cities over here, it's the same, right? But the first solution is much more elegant than the second one. But both work. Both are fine for me if you provide them as solution. The important is they work and they work correctly. Okay, now while. So we go up. While loop, we start here, right? So while loop 1.2.4.2, and while loops are being executed while the condition is true. So basically, while a condition is true, here the condition is true, so this is always true. The while loop never ends. And execute. An expression will be executed. Be very, very careful. It's very easy to get stuck in a so-called infinity loop. So an infinity loop never ends. That was me pushing too hard on the table. So an infinity loop makes your program being stuck somewhere, right? And you don't want that. Let's try it out. So while true, let's say I equals 0, while true, I plus equals 0.001, print I. Okay? So please take note, here on the, that is the left for you and me here, the bracket here is empty. When it is executing, right, when it is running, there will be a little star. When it is done, there's a number here, okay? So far, so good. So now I zoom out here a little bit because when I'm done waiting, right, when I'm out of patience, I will go to kernel, interrupt, right, to say, okay, enough is enough. I think you're in the infinity loop, and I put a stop over here, right? This ends here now, so to say. Good. Let's try it out. Do you see the little star in this box? It's executing. It's executing. It takes away my computing resources. Anyhow, so I interrupt, right? And then it tells me, oh, you interrupted in the while loop. That was always true. Okay, no worries. I meant to do this, right? I check what is I. I is almost 38,000. But I always was increased by 1 over 1,000. So what's 38,000 times 1,000? 38 million, right? So that loop ran just 38 million times, roughly, around. But it never finished. Okay. How do we finish this? So let's say while I is smaller, let's say 38 million, is okay? 38? No, sorry, 38,000. Like this, right? So while this is smaller, execute, right, add it up, at the end print I, let's see. Wait a little bit. Hope I didn't make a mistake with the it should end soon. Does it? I is smaller, yes. Is it doing something? Yes, here, you see. Good. So when it is larger than 38,000, it stops. And remember, there are rounding errors. Right, so our smallest unit we add is 1 over 1,000, but you see many digits, and that's because of rounding errors. Right, so they really add up if you execute many times a simple addition here. So far, so good. Okay, while loops, be careful. Okay, here's one more example. We start with a equal -5, the condition being true. I put here b for boolean. So then I say I equals 0. I start my while loop. The while loop is true, so I enter it. I print my condition, yes. Or then a semicolon means there's the next line. I plus equal 1, so then I becomes 1. If I is larger than 3, nope, we continue the loop, right? Go back here, we print the condition, we increase I, now I is 2. If I is bigger than 3, nope. Then we skip, right? Go back to the top of the loop, we print the condition, it's true, plus I, plus 1 of I, that is I equals 3. Is I larger than 3? No. And we go back to the top. Now we print the condition. It's the fourth time we print that condition, right? We add 1 the fourth time to I. Now I is 4. Okay? I equals 4. Is 4 larger than 3? Yes. So then we go into the if statements. You see this on the indentation, right? We enter the next inner hierarchy of our code. So we set there the B condition equal false. So not true anymore, it's false. Oh, okay, the loop block ends here as well. We go back to the top. We check the condition. The condition is false. We do not enter the while loop. We stop here. So far, so good. You want to try it yourself? Or too easy? Let's see. We can copy that code, put it in here, copy the condition, copy, paste. Very good. And first, right, copy, don't change anything, just execute, see if it works. Yes, it works. We even can check the value of I, right? I equal 4. Good. Now let's change something. How about we say we have here an A. Shall we make use of the A? How about A minus I minus 8? So that would be 0 minus minus 5. That would be quite big. So why do we only execute once? Now the loop. Can you see the difference? Can you see? So I put the minus I over here, right? So the thing runs like this. The condition is set to be true, right? I don't change the condition until I reach the head of the while loop. So I definitely enter my while loop. I print the condition. I add 1 to I. So I is now 1. I check, is this difference larger than 3? And 1 minus minus 5 is 6, and 6 is larger than 3. I set it to false. My condition ends here, okay? If I have here a plus, I run it a few more times, right? I run it basically 3 plus 6 times, maybe plus 1. So it should be 3 plus 6 plus 1. So how much? 3 plus 6 plus 1? 10. Okay? So you should see that 10 twos. You can count for yourself if you like. I'm not going to count now. Okay. While loop, right? Let's see what else do we have. What's going on here? Can anybody tell me what's going on here? What's that kind of a loop? Well, that is one of these infinity loops, right? Because I have while and true, I print something, I increase something, but I never change my condition. This is running forever. So what can we do with this? Let's say copy, paste, not execute, don't execute. We change a little bit because this time we are clever. So this time we make, so if A, if it's really large, right, 1,000, 100, we say break. And so a break statement is something a little bit more advanced than a simple loop, because within a loop, right, for a while, when we hit break, we say, okay, enough is enough, we stop the loop, something doesn't work out. So we see here, right, it goes to 100, and when we hit 100, then it's like, oh, enough is enough, stop this nonsense. It's most likely, yeah, what do we call it, infinity loop. So you can handle break. What else can we do? If a, let's go on top. So if we want not to print everything, just some certain values, right, we can say if a modulo 2, continue. And so the difference between break and continue is, at break, we stop the loop and we never look back. Right? At continue is like, hey, let's skip the loop. We don't stop, right? We're like, we still want to continue, but not for this value, right? So skip one round. Okay? So let's see what happens. Doesn't work. Then we'll just skip. Maybe something. So something is running. It shouldn't be like this. Can't see it. Don't worry. Interrupt. Anyhow, this was just extra, so you can also break and skip loops. Good. What else do we have? We have a zebra, a string, and then we have a list comprehension. I think you have seen this comprehension before. It's our expression, the for statement, the iterator, and the sequence, everything in a square bracket. So when we execute this, what we see? What's going on? Can you tell me? So let's copy and paste. So what's going on here? So in our list comprehension, right, we have the execution here, print C. But at the end, our output is none, 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 none. We had that before. We said don't overuse print. Use print only to follow what's going on. The print tells us here is every time we run over a character in zebra, we get just a character. But we can do this as well like this. And so the difference between my list of string and the string 1, so they're quite different. My list is this, and string 1 is this. Both, in principle, have all the words for zebra, just that here we have a string that puts them nicely together. Over here we have a list of each of the characters in zebra. Funny thing, they're both lists, so to say. So if you select the first element, they're actually the same. Just that your string is easier to read. I think there is a nice way of making this back into a string actually. So we have a list of characters. We can use the separator, that is a string followed by the join method with a list of elements here, and put them all together. Or you concatenate them, right? So far, so good. Yes, no, maybe. Okay. Let's continue. Where are we? So again, if you use print in an expression that's supposed to give you a result, right, you get nothing back. So the way to fix example 2 is you copy, you paste, and instead of print C, you just have C, right? Fixed. Good. What else we got? Example 3. And so this is the fix of example 2. Okay, and with this we actually at the end of this chapter 1.2 functions, loops, data structures, and so on. So right now, I hope you're able to know the difference between list, tuple, sets, and dictionaries, how to write a for loop, how to write a while loop, how to write an if statement, an if-else statement, an if, elif, and else statement. A list comprehension and a shorthand notation, an inline if, right, and a shorthand notation of the dictionary as well. And these are basically the most important parts. You have seen how to access elements of a list as well, individual elements. We call this indexing. We extend this later with the areas to indexing and slicing. But this will come in chapter 2, and chapter 2 is what? Let me see if I have here downloads. Over here. Chapter 2. Introduction to numerical Python. So this is where the main part of the course is starting. It, however, does not mean we are done practicing our basic Python. Right? So there's a lot to practice, a lot of hand-on exercises, homeworks we're supposed to work through to get familiar with how you put together these simple expression commands to get something more, well, practical, more intricate in its design, hopefully at the end useful. Okay, if there are no more questions about basic Python, we would now go into the second part. So we changed the course book from like lean Python to numerical Python. Also as an introduction, you can go through it. But we focus now on the numpy package, right, which is basically numerical Python and matplotlib library. Because we will handle a lot of numbers with numpy, and matplotlib, we will have simple access to put all the numbers into a graphical representation. Right? But we need to start learning how to use this. So let's see what's important here. So NumPy is designed for scientific computing, right? Numerical stuff. There's another one called SciPy, which is really good for scientific computing, but I think it's built on NumPy. The documentation is available on numpy.org. It's quite extensive. There are a lot of examples and there's a lot of explanations. Much better than I can do it here in the little time we have. So what can we do in NumPy? We can build n-dimensional array objects. Now this is really one of the key strengths when we can have an array that is one-dimensional, two-dimensional, three-dimensional, four-dimensional, and so on. And it's specifically designed to handle numerical data, so numbers, as efficient as, well, it is, I guess, possible in Python. Now it comes at a cost. Right? Python itself gives us great flexibility with its data structures. And we can mix and match. We can have nested lists of different lengths. In NumPy, we'll need a little bit more order. Right? We have well-defined arrays, matrices, right? 2 by 2, 3 by 3, 3 by 2, and so on. We don't have one column 3 elements and the next column 300 elements. No. Order, regularity. We only handle one data type, for example, and so on. But this then helps to make the code run a little bit faster. Okay, so we have an interface with C, C++, and Fortran. So why do we have it? Well, Python is not the fastest language because it's a high level of abstraction. C and C++ are much more designed on a machine level. Right? So it's a little bit harder to learn how to program, itself. Right? So you must think a little bit more like a machine, I guess. But it's much more efficient, right? Not a little bit. It's hugely more efficient. So all the big calculations at supercomputers where we use hundreds of CPUs, we run Fortran code, right? Or we run C code, preferably Fortran. Okay, nonetheless, we have therefore access to very fundamental scientific functions. We have access to Fourier transformation. We have access to random number generators. We have access to linear algebra, right? Matrix vector multiplications, and so on. Good. So how do we get NumPy? Well, first we need to install. But when I ask for the room, normally I ask the people to install all the packages because the moment you switch off the computer, everything gets deleted. So we have Python and NumPy already installed. Very good. Then we have to load the package. How do we load the package? This general syntax, so we would use any other package as well, is general syntax, import package name, that works. Or we use import package name as we give it a new name. Like you have a nickname for a friend or your pet. Don't call your dog dog. Right? Dog, come here. You give your dog a name, right? So you load your dog as something else. Okay. So let's see. If we only need a part, right? We don't need the whole package, then we would change it a little bit. We would say from package, right? Import just a specific part as something, right? From Zhongshan Dashui, import the Department of Materials and Optoelectronic Science. Way too long, that name, right? As MOS, right? MOES, right? Same thing, right? So you go down in the hierarchy and you only look into a specific part here. Plus you give it a much shorter name. Okay, so let's see how we do this with Python and NumPy. Okay, so here, import NumPy as NP. Easy. Let's see if it works. So I copy. Now I have here chapter 2, and I'm like, oh, this my worksheet here is already very messy. Let's make a new one. Copy, paste. Give it a moment for the kernel to start. Execute. I think it worked. So how do I know it worked? Well, first of all, there are no error messages, right? I can make a mistake on purpose. Numpy, or I try to load numpy, try to abort it. Okay, error message. Error message is very clear. Module not found error. It literally says here what's the problem, right? And then no module named numpy. When I look at it, it was like, oh yeah, I'm stupid here. Numpy also. Numpy. Okay, try again. So very good. How do I know that the numpy is working? I need to test it, right? So some basic things I can try. Numpy question mark magic symbol. Yes, I have a documentation. And here, so numpy docstring provides an array object of arbitrary homogeneous items. Homogeneous means same data structure, right? Okay. Fast mathematical operation over arrays. Oh, fast is very good. Linear algebra, Fourier transform, random number generators. Sounds familiar. If it does not familiar, go back to my slides. Good. Basically copy paste here. Good. So what else can we do with NumPy now? Very important. If you regularly work with codes and programming and other people's code packages, you need to be able to check what version of NumPy you have. I have version 1.24.3. What version do you have? Like version, like Windows 11, Windows 10, Windows XP. I have Windows 10. What Windows do you have? I don't really care, right? But what NumPy version do you have? That's what I care about. So what NumPy version do you use? Are you also using 1.24.3? Because I have not you have? Because I didn't update my Python quite a while. At least on this machine. Is it really 1.24.3? Yes? No? Okay. Okay, so what else? So if you don't have NumPy, you would actually go to your Anaconda Navigator or your Anaconda Terminal, whatever you have, check the environments, look for NumPy, and then CCC. Okay, here it tells me also I have version 1.24.3. It also tells me that I should update my version, right? It's out of date, update available. So when you have a more recent installation, you have a different version. So far, so good. Okay, so what else can we do? Let's stick to the slides for once. Loading. The first load, yes. Here, we also want to load matplotlib, right? That is the one for plotting. So we can do the same thing, import this one. Let's try something here, right? Because, so we can actually modify this a little bit from matplotlib import pyplot as plt. So you can try the version I gave you. We also can look at the example. Both should be equivalent. So again, it's programming, so many different ways can give you the same result, but make sure whatever you have is correct. So I could, for example, check if I have a documentation. I can't read this because I zoomed in too much. Yes, I have. I can check my version. Okay. Has no version. Unbelievable. So why has it no version? Because actually, big module is matplotlib, right? And that one comes with a version, I hope. Ta-da! Alright, so this one is version 3.7.1. So when you have your Windows, right, Windows comes with a version. Nobody really cares what Notepad comes with a version, right? We just have Notepad. But the same here, right? So the big package comes with a version where you keep track of everything, and then whatever sub-module is, of course, part of that version. So far, so good? Good. So what else can we do? Now we have like 15 more minutes. I can do a little bit. So here I have a slightly different example of import. So here from numpy, we use star. And star here means we import everything. Okay. It's not much different than before. Just that we don't call it now np. If we have done this, we can also ask for the version. We can also ask numpy to be imported as np. Ask for the version. Do you actually see when I made the slides, I had version 1.21.5. So when I update it, I'll never update again here. It's okay. The difference between the import everything and import numpy as np is if I import everything, I don't need to specify it anymore. It is known under the name as a given in the package. And then version is just accessible, whereas numpy as np, I need to call the main object and then ask for the attribute through a dot, and then the attribute version. Okay, so far so good. So now, numpy array object. This is one of the big things in numpy, the arrays. So arrays can be assigned to instances with the array method. So let's try. Let's try what this means. So we have numpy loaded, right? To get access to the array method, we need to call numpy and full stop array. Let's check the documentation. So it wants to have an object, right? Okay, so we can give it an object. No worries. What is this? This is big. How to make this smaller? Maybe just go back here. Okay, good. So when I call this on an empty list, well, I get an array object, right? Which is empty, but it's an array. So far, so good. Let's see what else. The arguments can be list of one-dimensional arrays or nested list of multi-dimensional arrays. Okay, let's try. So we have here an empty list. I can put in one dimension, right? And I can put in nested lists. So 3, 9, 8, 7. So I have two three-dimensional lists here, right? So I have two lists inside here, each having 3 elements. So what I get in the end is something that looks almost like an array 3 by 2. Okay, so multi-dimensional seems to work. What else do I have? A dimension of an array is referred to as an axis. Okay, so when we want to have the columns or rows, right, we call them in numpy axis. Arrays are used to store numerical values. Okay. So then you can say, hey, I don't believe this. I don't believe this, and you will not be utterly wrong. How about I have an array with A? Ah, this also works. Interesting. But how do we say this? NumPy is smart enough to actually address this as a different data type. So if we have really numerical, yes, values need to be a list. Make sure that just now I actually saw the data type here. So NumPy assumes normally a float data type. Right? If it can simplify, it will put integers here. Let's see if we can access this. So I can ask for the attribute of the data type by just adding a dot here, and it will tell me, oh, your array is in 32. So then NumPy can simplify the data type it will. If it cannot, right, if it's not a float and doesn't fit in this one, it will give special data types. Let's see what else we can do. We also can have a Boolean data type. Right? So the Boolean data type I, for example, use frequently just to filter data. Right? When I have gigabytes of data, I have a conditional statement, and then I filter the data, apply the filter to my data to get just a small portion of that data. Good. So the statement that we are using numerical values, well, it's correct because it doesn't say we store only numerical value, but the arrays are actually intended for numerical, for numbers, not for letters. There are other things that work better for letters. What we cannot do is mixing numbers and letters. We can. Oh, what happened? Am I talking nonsense or what's going on here? Are we mixing numbers or letters? Look carefully. So NumPy and Python try to be as helpful as they can, always. I give here which data type? Integer, right? And here is string or character. So Python is like, what do I do? What do I do? So they assume the most general case. Right? And the most general case is I take the number, I make it a string. Because I don't know how to put the string into a number, right? So I do the opposite. So and then when my array at the end becomes a string, right? Not a number anymore, not an integer. It symbolizes a number, but the data type here is a string. You see this on the two quotations. And here the end. What else can we do? 9.0. Also here, right, we have what data type? Integer and a float. Python is like, what do I do? Integer and float takes the most general one and puts both as floats, right? Because you always can put back you always can add zeros to an integer to make it a float easily. The other way, you need to round, you need to cut. It's not very well defined which one is the one to apply. Okay. Anyhow, so NumPy array object has some attributes as well: shape, size, endim, and dtype. So the data type we saw already. Let's look into the shape. Oh, that is 2, like a vector, right? So just 2 elements in my vector. How about here in my 3x2 matrix? 2x3, very good. What else do we have? We have endim, the number of dimensions, right? You know this. I think you know this as the rank of a matrix. Right? 1 dimension is a vector, 2-dimension ranks is a normal matrix, and then everything larger is a tensor. Okay, what size? test the size. So here the size is 6, down there the size is 2. This is just the number of elements in your matrix. So far so good? Very good. So numpy arrays can support numerical data types. Data types cannot be changed after creation of array, but typecasted. And we can have different sizes, right? But we still must arrange them in regular representations. So meaning if you have 10 elements, if you have a 2 by 5 matrix, you cannot make it into a 3 by 3 matrix because the size is too much. Once you have 10 elements, once you have 9 elements, where is your extra element? What happens? But you can change your 5, not so much option with 10 and 5 and so on. You can always change it in 1 times 10, right? Or 1 times 9, the other one. But you must account for all your data when you change shapes. Okay. Now we go down. What else do we have? Right, so we can pass nested lists to the array function to get a matrix, right, or array. There are actually different data types for matrices as well in NumPy. We'll do this later. And the data type is ND array, right? So n-dimensional array. N because we can have different dimensions. Let's see what else do we have. We can check the shape and data type. Did this before just now. So this is more interesting. So the general syntax, lastly given, is here. For us, very interesting is the object. So this is the list or the nested list we use, and then there are some standard arguments used. dtype is somewhat interesting. So let's see in the last 3 minutes what dtype is doing. So dtype normally is none. Let's take our nested list over here. Copy this for our array. Put in this information. Close the bracket here. Nothing new, right? Everything works fine. Let's change. Let's use integer. Same result because while we give integers, we get integers back. But if you already know that the numbers should be actually floats, we can change this right here. And you see this, that the numbers suddenly carry the decimal dot. Let's see, can we use complex? We can make it complex numbers and add a 0 imaginary unit at every number. Let's see what else we can do. How about string? And we can make it into strings. All just by giving this additional optional argument. That's an optional argument. You can give it. You don't have to give it. But if you don't give it, then Python will make a choice for you, right? Okay, so far so good. And right, so there are other optional arguments that you can explore if you like. For us, most important, object and data type. Let's see, and then we should. The rest we can then start next time, or continue next time, I should say. So after the break, we will continue. We will continue our worksheets or the practice, and you should be able to solve the entire worksheet. Right, you have another hour. Remember, there's also a home assignment that is due on the weekend. And if you have any questions, then just ask. Okay.